Hello. Good evening, everyone. Good evening. Am I audible? Okay. Fine. So in my last lecture we have talked about the basic introduction and the classification of amino acids. So there we have seen different types of means what are the basic features of amino acids and how these amino acids are going to be classified. So we have seen 4 different types of classification schemes. So we have classified amino acids on the basis of 4 criteria. The first criteria was on the basis of R groups. So we have seen every amino acids is having one amino groups, one carboxylic groups, and one H group and one R group. So R group is going to vary from amino acid to amino acid. So different amino acid will have different types of R group. Now according to R groups, because these different amino acids having different types of R group, so according to R groups we are having different types of properties. Because R group is from all the 20 amino acids, we are having 20 different types of R groups. So 20 different amino acids we are having. Now on the basis of R group we have classified amino acids on the 4 different criteria. First criteria was which type of R group they had. So on the basis of R groups we have classified into 7 classes. Those classes were, first, if amino acid is having their R group will be aliphatic. So we had 5 amino acid was there. That was glycine, alanine, valine, leucine and isoleucine. Second class was OH containing amino acids. There we had 3 amino acids, that was serine, threonine and tyrosine. Then we had sulfur containing amino acids. 2 amino acid was there, that was cysteine and methionine. Then we had acidic amino acids and their derivatives, that there we had glutamic acid, aspartic acid and their amine derivative, that is glutamine and asparagine. Then we had basic amino acids. There we had 3 amino acids, that was lysine, arginine and histidine. Then we had aromatic amino acids, that was phenylalanine, tyrosine and tryptophan. And last class was amino acids. There we had proline. So this was one scheme. Second classification scheme which we have discussed previously, that was on the basis of polarity. So we had 4 classes. There we had polar amino acids, non-polar amino acids, positively charged amino acids and negatively charged amino acids. When we are talking about positive charged amino acids, there we are having basic amino acids only, because base normally have positive charge. So if you see the structure, so these are the basic amino acids which is having positively charged, which is having extra positive charge, like here you can see it, here you can see it, here you can see it. So these are having positive charge. Good evening everyone. Good evening Ajay. Good evening Rajat, Nivans. Good evening everyone. Now so these are the 4 classes: polar, non-polar, positive and negatively charged. Third classification scheme which we have discussed was on the basis of essentiality. It is nutritionally essential or non-essential. There we had only 2 classes. It was essential amino acid and non-essential amino acid. For that one I had given you a kind of mnemonics, that private team hall. So you can remember 10 essential amino acids, remaining 10 will be non-essential. And the last scheme which we have discussed, that was on the basis of the fate of amino acids. So there we had 3 classes. It was only ketogenic, only glucogenic and both ketogenic and glucogenic. So leucine was the amino acid which was only ketogenic. 5 amino acid was there which was ketogenic, glucogenic, and 14 amino acid was there which was both ketogenic, glucogenic only. So that we have already discussed it. So today we are going to talk about the physicochemical properties of amino acids. So we will see different type of properties. So this is the basic structure of amino acid, which we have seen it. So in the amino acids, I have already told you we are going to have only alpha amino acids in our body for protein synthesis, and that all only L type. No D type amino acids we are going to use for protein synthesis. So only alpha L amino acid we are going to use in our protein synthesis. Now, so this is alpha amino acid because this is the carboxylic acids, and this carbon will be the alpha carbon, and whenever alpha carbon will have amino group, it is called as alpha amino acids. So depending on where amino group is attached, it is attached to the alpha carbon or it is attached to the beta carbon. So on the basis of that one, we are going to call it alpha amino acid or beta amino acids, right? So this is our amino acids. So if you will see this amino acids, every amino acid is having this group common. So this is common features in all the amino acids, means minimum they will have one amino group, minimum they will have a carboxylic group, they will have a hydrogen atom and a central carbon. So this is common for all the 20 amino acids. Then what is the difference? All the 20 amino acids which we are going to use for protein synthesis, they differs in their R group. So different amino acid will have different type of R group, means the final properties, which these are the 20 amino acids we are having. So you can say every amino acid having this portion is common. So this is common portion. So any properties which is because of this common feature, common components, any properties which is due to this one, so that will be shown by all the amino acids, because every amino acid having this portion present. Now then different amino acids are going to have different type of properties also, like glycine behaves differently than the alanine, alanine behaves differently than tyrosine, tyrosine behaves differently than cysteine, and that difference in their properties is mainly because of their R group. Means if you'll go, you can see here, so amino acids are going to show you different type of properties. Those properties are either due to this group, amino group, or due to this carboxylic group, or due to their R group. Whenever amino acid show properties because of this amino group, so this will be shown by all the 20 amino acids. Nivans, where is the fifth amino acid? Okay, you are talking about in alpha helix. Nivans, you are talking about the alpha helix, right? Because I have told you long back, whenever hydrogen bond forms, that time distance between two atoms which is going to form hydrogen bond, that distance should be fixed. If you will enlarge the distance, means distance will be large or distance will be small, hydrogen bond will not form. So distance should be fixed, and that fixed distance is going to be formed in your alpha helix when first amino acid and the fifth amino acid. So this distance is perfectly fit for the formation of hydrogen bond. If this distance you will enlarge, like we are going to form bond between first and sixth, so distance between large, big, so that hydrogen bond will not form, or first and third, then distance will be a small, so that time also hydrogen bond will not form. So distance should be perfectly fine, perfectly fixed, so that hydrogen bond will form. If it will have more distance or less distance, hydrogen bond will not form. Fine? Is it okay? Okay. Now I have told you this is the basic structure of amino acids, and amino acid only going to give you proteins. So this is present in every amino acids. This is the basic properties of every amino acids. So every amino acid, all the 20 amino acids have this amino group. Means any properties, any characteristic feature which is shown by this amino group, that will be present in all the 20 amino acids, because all the 20 amino acids have this group. So any properties which is because of this amino group is present in all the 20 amino acids. Similarly, this group is also present in all the 20 amino acids. So any properties which is shown because of this group is also shown by all the 20 amino acids. Means any properties, any character, any characteristic feature, any kind of chemical reactions which is due to this amino group and this carboxylic group, that is shown by all the 20 amino acids, because that is common, that is present in all the 20 amino acids. Now all the 20 amino acids, they differ in their R group. So this is different, 20 different types of R group we are having. So every amino acid behaves differently, and that is only because of their R group. Like some chemical reactions is shown by tyrosine, not by alanine, not by valine. Some chemical reactions were shown by cysteine, not by methionine. That is only because of this R group. So amino acids differ in their R groups, and that makes different type of chemical reactions. Now, so we are going to see the chemical reaction in three different ways. Like first, it is the physical properties, where we will talk about the solubility, melting points, test which type of how it looks like, their optical properties, Zwitterion and isoelectric point, and titration curve. So this is the physical properties of amino acids, that is common for almost all the amino acids. Then we are going to see the amino acid structures, where we will see any chemical reactions, any properties which is caused due to amino group, chemical reaction which is shown due to this carboxylic group, that we will see. And then we will see some chemical properties, chemical kind of, you can call kind of color reactions which is due to their R groups. That we will not talk in the details, but we will see in only names. Good evening Ayatasham, good evening Anjali. So first, any chemical, there are certain chemical reactions which is shown by carboxylic group, means acid group, that is the properties of acidic groups, like decarboxylations. We will see in the details. Reaction with the any kind of base, any alkali, so salt formation will be there. Reaction with the alcohol, there we will have esterification, ester formation will be there. And lastly, reaction with the amine groups, so amine will be there. And then some kind of chemical reaction which is caused because of amino groups, means basic groups. So there also we will have salt formation, hydrogen reactions, which is the characteristic properties for all the alpha amino acids, color reaction for amino acids, transamination and deamination. These are the different properties of amino acids, which is because of amino groups. Now first come to see the physicochemical properties of amino acids, where we will see its first is solubility. Normally amino acids, because you have seen the structure of amino acids, so it is having amino group also, it is having carboxylic group also. So because of carboxylic group or because of amino group, it is water soluble. Any compound, any chemical compound which have a tendency to form hydrogen bond are water soluble. Any compound, any chemicals which can form, which have a tendency to form hydrogen bonds are water soluble. So here also amino acids have amino group, that is NH2 groups, they can form hydrogen bonds. You know that nitrogen can form hydrogen bonds, or COOH, this OH can form hydrogen bond. So because of this hydrogen bond formations, these amino acids are water soluble. So they are soluble in water. Whenever means water soluble means they are polar in nature. Because they are polar in nature, so they will be insoluble in organic solvents. So solubility you have understand. any chemical reactions which can form hydrogen bond with water are water soluble. This amino acids, whatever we are going to say, they have both two types of groups which can form hydrogen bond, that is amino group as well as the carboxylic groups. So because of that one, they are water soluble. So amino acids are water soluble, means hydrophilic in nature. Any hydrophilic compounds will be hydrophobic in nature, means they any hydrophilic substance will be lipophobic, means they are not going to soluble in lipids. So this is amino acids are water soluble, lipid insoluble. Clear? Is it clear to everyone? Second property is their melting points. Melting point means normally whenever we are having a substance have different physical forms, like it will be in solid forms. If you are going to give heat, solid becomes liquid, and if you are going to still give the heat, liquid becomes gas, vapor. So different physical form, physical components, features, phases they are having. So solid, liquid, gases. Amino acids also normally it is solid structures. Akshay, what to repeat? Can you tell me? Solubility, I will repeat it. Let me finish melting point, then I will repeat it. So melting point we are going to call whenever a solid substance will be liquefied, means it will change their physical structure one from solid to the liquid. So we are going to call them melting temperature. Yeah, melting point, the temperature at which solid is going to be converted into liquid. So melting, that means solid melts into liquid. So that is called as melting temperature or melting point. In the case of amino acids, almost all the amino acids have very high temperature. Melting point is very high, means they are not going to be melt at 100 degrees centigrade or around less than 100 degrees centigrade. Melting temperature will be above 200 degrees centigrade. So the normal melting temperature, melting point, the temperature at which amino acid becomes liquid, that is more than 200. Now, so this is called as melting temperature. So remember, amino acids have very high melting temperature, that is more than 200. Now, solubility, again I will tell you, any compound, any chemical which have a tendency to form hydrogen bond with water. Hydrogen bond you are knowing, in our chemistry we are having three most electronegative elements are fluorine, oxygen, nitrogen. So these three normally forms hydrogen bond. So whenever fluorine is associated with hydrogen, or oxygen is associated with hydrogen, or nitrogen is associated with hydrogen, so whenever hydrogen is linked with any of these three atoms, these three means high electronegative elements like fluorine, oxygen, nitrogen, and nearby either oxygen or fluorine or nitrogen will be there at a fixed distance, not too far, not too near. So there will be a hypothetical attractive force. Yes, there will be attractive force works between this hydrogen and this oxygen, fluorine or nitrogen. So this hypothetical force is called as hydrogen bond. So in the amino acid we are having NH2 group, amino group, and we are having COOH group. So we have this also and this also. This is OH and this is NH. So both groups can form hydrogen bond. So any compound which have a tendency, which have a power to form hydrogen bond with water, they are water soluble, because water solubility is because of hydrogen bond formation only. So here amino acids have hydrogen bond formation power, bond formation capacity. So because of that one they are water soluble. and any substance which is water soluble will be insoluble in lipids, because water is polar and lipids are non-polar. Lipids means organic solvent, non-polar. So amino acids are soluble in water or polar solvent and insoluble in non-polar, lipids or organic solvents. All three are of same nature. Is it clear, anyone? Now, next property is their test of amino acids. Every amino acid is having some or a specific test. Whenever we eat it, it will give you a specific kind of taste. So, like and some of the amino acids are sweet in taste, some of the amino acids are tasteless, they don't have any specific taste, or some of the amino acids are bitter in taste. Like amino glycine, alanine and valines are sweet in taste, whereas leucine does not have any taste and arginine and isoleucine is having bitter in taste. Now, one of the compound that is called MSG. Can anyone will tell me what is the full form of MSG? What is the full form of MSG? Messenger of God. MSG means messenger of God. Is it? Or something else? No. MSG means monosodium glutamate. Good. Everyone you people are eating Chinese food, either noodles, then Manchurians, different Chinese food you are going to eat it. In that one, normally in the Chinese food we are going to use a salt sugar like a compounds that is called as MSG. That is monosodium glutamate, means it is a derivative of glutamic acid. So it is called as, its name is monosodium glutamate. In short form, in common name is Ajinomoto. So this is commonly used in Chinese food as a taste inducer. It induces the taste. So it normally works on our taste bud, on our tongue. We are having taste buds. This monosodium glutamate or Ajinomoto works on our taste buds and increases the taste sensation. So yes, Ajinomoto, yes. So this normally increases your taste. So every Chinese food normally every people likes it because of this monosodium glutamate only. But if you will use this monosodium glutamate too much, it will also going to cause some disease. That disease name is Chinese restaurant syndrome. So in that case, normally our taste buds are non-functional, it will be ineffective. So that is called a Chinese restaurant syndrome, which is caused because of higher use of or more use of monosodium glutamate. So this is because of their taste. Now optical properties. Yesterday also we have seen it. Every amino acid have a central carbon, and central carbons, along with central carbon we are having 4 single bonds, and 4 single bond is having 4 different groups. Like one side it is having COOH group, other side it is having amino group, third side it is having hydrogen, and fourth side it is having R group. So this is the central carbon. So this central carbon which is having 4 single bonds and 4 different groups are associated there, means this carbon is asymmetric carbon. So yesterday I have told you to remember 2 rules when to call a compound asymmetric. For that one we have 2 rules. First rule is carbon must have 4 single bonds, means no double bond, no triple bond. So in this case, if you will see in this compound, this carbon, we are having this carbon and we are having this carbon. So first talk about this central carbon. So the central carbon is having single bond only. This is single bond, this is single bond, this is single bond, and this is single bond. So this is first central carbon is going to follow my this rule. Fine. Now second rule is all the four groups, four substituents associated with those four single bonds should be different. Like this H is different from this amino group, this amino group is different from this R group, and this is different from CH group. So when four different groups are linked there, it means this compound is going to follow my this rule also. Means whenever they are going to follow your both the rules, it means compound carbon is asymmetric, and asymmetric carbon gives you different kind of stereoisomers like D form, L form, different other stereomers also. So on the basis of this one we are going to decide it. Now if you go to see this carbon, this carboxylic carbon, so can you decide it is asymmetric or it is symmetric? The central carbon of this carboxylic acid carbon is symmetric or asymmetric, and which rule they are not going to follow? We have two rules, rule number 1 and rule number 2. Can you tell me this carbon is symmetric or asymmetric, and which rule this carbon is not following? Anyone? Can anyone tell me? Asymmetric. How it is asymmetric? Anyone tell me? You have to tell me. So we are having two rules. First rule is carbon must have four single bond. Single bond. No double bond, no triple bond. So carbon should not have any double bond or should not have any triple bond. Can you see in this carbon any double bond or any triple bond? Yes, this carbon is having one double bond. So whenever a carbon will have minimum one double bond or one triple bond, it is symmetric. Everyone is saying asymmetric. No, this carbon is symmetric carbon. Why this is symmetric carbon? Because this is not going to follow my first rule. So it is having one double bond. Oxygen is associated with the double bond. So whenever double bond will be there, means carbon is symmetric. So to be asymmetric, both rules have to be followed. Means no double bond, no triple bond, and all the four groups, four things associated there should be different. Clear? Like I am going to write another compound. This carbon is symmetric or asymmetric? This carbon which I have written here is symmetric or asymmetric? And if it is asymmetric, why it is symmetric? If it is asymmetric, why it is asymmetric? You have to tell me about this carbon. This is symmetric, right? Correct. This carbon is symmetric. Why? Because here we are having a double bond. Perfect. So this carbon is symmetric carbon because it has a double bond. Now I am writing here a acid, amino acid on the top. This is having a central carbon. It is having four groups associated there. Can you decide it is symmetrical or it is asymmetric? This one which I have drawn here is symmetric or asymmetric? it is amino acid because it is having amino group also, it is having carboxylic group acid or carboxylic acid also group also. So it is amino acid because amino and acid group. It is symmetric or asymmetric. Top one. Symmetric. Akshay, look at again. Akshay, look at the picture again and tell me it is symmetric or asymmetric. I have not written, in this case I have not written R. Anjali, I have written a central carbon, 4 single bonds and 4 groups, H, COH and H2. So rule number 1, carbon should have 4 single bonds. Yes, so it is having 4 single bonds. So rule number 1 is followed. Rule number 2, 4 groups associated there should be different, but in this case they are not different. This group is same as this group. So when 4 groups are not different, it is symmetrical. So now you may look at 4 different groups and how to decide it is symmetric or asymmetric. Fine, perfect. Then whenever we are having we have find that it is asymmetric carbon, then we can go for nomenclature, that is how to do nomenclature. It is D form or it is L form. So yesterday also I have told you, you can watch that video also, how to do nomenclature. So if we are going from lower atomic number to the higher atomic number side, like 1, 6, 7, hydrogen 1, carbon 6, nitrogen 7. So we are going from 1 to 7, lower atomic number to higher atomic number, and if that direction will be anti-clockwise, we are going to call them levorotatory, left-handed side. So it is opposite means anti-clockwise, levorotatory, left side. So whatever you want you can call it, but it will have L. Whenever we are going from 1, 6, 7, if the direction of movement from lower to higher atomic number is right-handed direction, clockwise direction, we will call it D form of amino acid. Fine. So we have, because this is asymmetric carbon, so only those compound will have D form or L form if it is having asymmetric carbon. Any compound where you have minimum 1 asymmetric carbon, then only D and L you have to think of. If no asymmetric carbon, no stereoisomers, no D form, no L form, means glycine, which I have written here, this compound is symmetric compound, no asymmetric carbon, means they will not have any D form, they will not have any L form, so no stereoisomers. And this is the structure of glycine. So glycine is the only amino acid which does not have any stereoisomers, means they don't have any D form, they don't have any L form. So glycine is having only one structure, not stereoisomers. In our body, whatever amino acid we are going to use for protein synthesis, they are alpha L amino acids. Never we use D amino acid for protein synthesis. Then D amino acid, where we can find out? We can find this one in the bacterial cell wall. Microbiology, if someone is from microbiology, they can tell you D pimelic acids or some other amino acids we can have in the D form, that is in the bacterial cell wall. Otherwise, normally in the protein synthesis we are not going to use D amino acids. Clear? So all the amino acids which we use in the protein synthesis are of alpha L amino acid. we are not going to use any D amino acid for protein synthesis except glycine, because glycine does not have L form or D form. So otherwise rest other 19 amino acids we are going to use only L type of amino acids. Now we have seen amino acids have amino group, that is basic group, and this is acidic group. So the properties of base or basic group is they have a tendency that it can accept one hydrogen ion, so it can take one proton. Or acid have a property that it can donate one H plus. So whenever this base will accept one H plus, it will be converted to NH3 plus, and if acid donates their H plus, it will be converted to COO minus. So any compound which have both positive charge and negative charge together on the same compound at the same time, overall charge will be 0. In this case, one positive charge, one negative charge, means overall charge is 0. So this is going to counter this one. So overall charge is 0. This is electrically neutral molecules. So this type of a structure we are going to call it Zwitterion. Zwitterion are those ions where compound have positive charge, negative charge together at the same compound at the same moment, same time, so that compound will be electrically neutral. It is called as Zwitterion. Correct? So a Zwitterion is a compound with overall no electrical charge, but contains positive and negative both type of charges. So it will have positive charge, it will have negative charge, but different places, different locations, but overall it is 0. So that is called a Zwitterion. Amino acid does not form Zwitterion at every pH. Amino acid gives you Zwitterion only at a specific pH. So that is fixed for every amino acids. So glycine will be in the Zwitterion forms at a specific pH. Tyrosine will be in the Zwitterion form at another pH. So for every amino acid we are having a different separate pH as their means Zwitterion form. So the pH at which any amino acid exists in the form of Zwitterion is called as isoelectric point or isoelectric pH. So the pH at which amino acid exists in the form of Zwitterion is called as isoelectric point or isoelectric pH. What is Zwitterion? A ionic forms of a compound which will have both positive charge, negative charge together on the same compound at the same time, so that compound will be electrically neutral, overall charge will be 0. So that is called as Zwitterion. Is it clear? Now this is a compound, this is an amino acid which we can say here, like this is having amino group also, this is having acid group also. Now both the groups have different property, man. This group can accept one H plus, this group can donate one H plus, as you know. Yes, this can accept H plus, this can donate one H plus. Now whenever we are going to take this amino acid at lower pH, means towards acidic pH, I'll tell you, we are going to talk about isoelectric pH only. So whenever we are going to take this amino acid at lower pH means at acidic pH. Acidic pH means pH less than this pH. This is going to exist at a specific pH. So if you are going to take this amino acid at lower pH, means towards acidic side. So acidic side means medium will have more H plus available. So in the medium we are having more H plus available there, and when H plus is available there, we have this amino acid in this high H plus medium. So which group will take H plus? If you are going to put this amino acid in the acidic medium, so which group is having tendency to accept H plus, this or this? So amino group is having a power to accept H, so it will take that extra H from the medium and it becomes NH3 plus. Means whenever you are going to take amino acid to acidic pH, amino acid will be positively charged. Means amino acid will have positive charge on their surface, as you can see here. So at lower pH, amino acid will be positively charged. Now if same amino acid, this amino acid we are going to take on other side, means higher pH side. Higher pH means alkaline side. So in alkaline side we are having low level of, we are going to have low level of H plus ion or high level of OH minus ion. So what will happen at that particular lower pH means acidic pH, we are having a pH scale. In this pH scale, this is the 7 pH. If you are going towards lower pH side, this is pH scale we are having from 0 to 14. So if you are going, this is the neutral pH. If you are going this lower pH, means this side 0 to 7 we are having acidic pH, acid, and 7 to 14 we are having alkaline pH or basic pH. So low pH means less than the 7. I am talking about acidic pH. High pH means alkaline side towards 14. Low pH means towards 0. High pH means towards 14. So when we are taking amino acid towards higher pH, where we are having alkaline side, in that case either I will have low H plus because it is alkaline medium, so H plus concentration will be low, or we are having high amount of OH minus. So in that case this group have a tendency, because we are taking this amino acid to a low pH medium, low H plus medium, so their H plus will be donated from this one. So this group, acid group, has removed their H plus, so it will be converted into COO minus. Means two things you need to remember here is, whenever you are going to take amino acid to a lower pH, means towards acidic side, amino acid will be positively charged. Whenever you are taking amino acid towards higher pH, towards alkaline side, amino acid will be negatively charged. So remember this one. In between, so at this, between this pH and between this pH, there is a specific pH. Between this and between this, there is a specific pH, a specific place where amino acid exists in this deuterion form. So amino acid exists in this structure which will have both positive charge and both negative charge. That particular pH, between this pH and between this pH, we are having called as deuterion existence, and where deuterion forms, that is called as isoelectric pH. Means between the acidic pH and alkaline pH there is a specific pH at which amino acid exists in the deuterion forms. That particular pH we are going to call it isoelectric point or isoelectric pH. In short form we are going to denote it in the form of Pi. Is it clear? Is it clear to everyone? So the isoelectric point is the pH, or isoelectric pH is the pH at which the net charge on a protein or amino acid is 0. Means the pH at which your amino acid or protein exists in the Zwitterion forms and overall charge will be 0. It is called as isoelectric point or isoelectric pH. And normally, remember, whenever a amino acid or a protein reaches to its Zwitterion forms, Zwitterion pH, protein is going to be denatured. It is going to be solidified, precipitated. Okay, again I am repeating. This is your amino acid. This amino acid is having two specific group. One is COH group, other one is NH2 group. Whenever we are going to take this amino acid at lower pH means towards acidic side, where acids, this low pH means acidic side means we are having more H plus is available into the medium. It means H plus is sufficient available into the medium. So we are having a beaker. In this beaker we are having acidic environment, and there we are going to put this amino acid. So what will happen? This amino acid is here. In this medium we are having sufficient amount of H plus is there. It means some group amino acid, if it will have a tendency to accept H plus, it will accept it. So this amino acid is having two groups. One is this one, other one is this one. So this group is going to accept H plus. So it will be converted into positively charged structure, positively charged form. So amino acid becomes positively charged. Similarly, if you are going taking towards other side, alkaline side, where low pH will be there, means pH is high and alkaline medium means it is H plus concentration is very less, or OH concentration is very high. So OH is high, H plus is low. In that case, COH group is going to release their H plus. So it will be converted into negatively charged molecules. So at higher pH, alkaline side negatively charged. At lower pH towards acidic pH, it will be positively charged. In between, whatever pH is this one, whatever pH is this one, in between we are having a specific pH where both positive charge and negative charge exist on your amino acids. So that pH we are going to call it isoelectric pH. The pH at which amino acid or any compound have both positive charge and negative charge together, and overall it is 0, means same number of positive charge, 1 positive, 1 negative, 2 positive, 2 negative, 3 positive, 3 negative, equal number of positive, equal number of negative, and that we are going to call it isoelectric pH. Is it clear, Ehtazam? Now we are going to see how to calculate isoelectric pH, isoelectric point. So here is a amino acid. So in this case amino acid, you can see this is the central carbon. So this carbon is the central carbon. So it is having one R group as a methyl group, one H, one amino group, and one carboxylic group. So this group is also going to ionize at a specific pH, means the pKa, that is called dissociation coefficient of one group is 2.3 pH. Dissociation constant of this basic alkaline group is 9.69 pH, means we have two groups and both the groups have two dissociation coefficient, dissociation constant. So if you are going to get any such question in the different places, either in the competition or anywhere, where amino acid will have only two dissociable groups, two groups which can be ionized, which can be dissociates, and we have given you 2 pH. In that case, you don't have to do too much of effort. You just take the average of both the pH. If this condition is applicable only for those amino acids where only 2 groups are there, 2 dissociation constant is there, 1 and 2. So in that case, just take the average of both the pH, and that will be the isoelectric pH of this amino acid. So the Pi value can be calculated by taking the average pKa value of corresponding to the ionizable groups. So simple. If you are having such type of compound, such type of amino acid where only 2 dissociable groups are there, and we have given you both the pH, both the dissociation constant, in that case just take the average of that pK value. It is as simple as. Difficulty will come when we are having 3 or more than 3 ionizable groups. Like this is an example of aspartic acid. In this aspartic acid, like say we are having pH 0 to 14. So if we are going to take amino acid at any pH, you can put your amino acid at 0 pH also, you can put amino acid at 14 pH also. And so yeah, this is for you only. So you can put your amino acid at any pH from 0 to 14. But there will be some specific pH value. For time being, we assume this pH is the isoelectric pH of by amino acid A. So if you are going to take your amino acid at this place, it will be in the Zwitterion form, because this is the isoelectric pH. If you will take this amino acid lower pH than this one, means towards 0 side, it means this will have only positive charge. This will have be positively charged. If you are going to take this amino acid towards alkaline side, it will be negatively charged. At this pH, isoelectric pH, it will be have both positive and negative. It will be electrically neutral. So for every amino acid we are having a isoelectric pH, and that pH is varying according to amino acid to amino acids. So different amino acid will have different isoelectric pH. That we have to calculate, that we have to estimate when groups. Like you can see this amino acid. In this amino acid we have 3 groups which can be ionized. Like one group which can ionize, second group which can ionize, and third group which can ionize. In this one you have to remember one thing. Whenever you will take this amino acid at lower pH, it will be positively charged, means most protonated forms, maximum protons. Wherever proton can be added, every places proton will be added. In this case, this amino acid is not in the most protonated forms. Question only, Nivans, it is question only. I am going to calculate the isoelectric pH of this amino acid. So this is question only. So in this case you can see here, you can see here, this amino acid is having 3 ionizable groups. One is this one, second one is this one, and third one is this COH group. So all the 3 ionizable groups ionizes at different pH. Like this group ionizes at pH 2.1, this group ionizes at pH 9.8, and this group ionizes at pH 3.9. Now whenever we will keep this amino acid at lower pH, in this case we have 3 pH, 9.8, 2.1 and 3.9. So 2.1, 3.9 and 9.8. Which one is the lowest pH? Among three, the lowest pH is 2.1. So what we are going to do? We are going to put this amino acid lower pH than 2.1. Like I can put it 2, I can put it 1.5, I can put it hypothetically. I am not going to take and put it in dip it in amino solutions, but we are going to take this amino acid and put a pH which is less than the lowest dissociation constant pH. So for time being, I am going to put this amino acid in the lower pH, lower than 2.1. In that, at that particular pH, like I am going to put it 1.5 pH. So at 1.5 pH, this amino acid will be in the positively charged condition. It will be positively charged. Positive charge means which group can take positive ion? Can you tell me which group will take positive charge? This is this group, this is acid group, this is acid group, this is alkaline group. So this group can donate H plus, so it is going to be negative charge. This is also going to donate H plus, so it is also going to be negative charge. This is going to accept positive charge, so it can accept H plus. So the most protonated forms of this compound, this amino acid, is when this NH3 and it will have a positive charge. This is the most protonated forms. This amino acid cannot accept extra proton now. Maximum proton now it is having. Yes, perfect. So I have added there. So if you are going to take this amino acid any pH which is less than 2.1, like 1.5, this amino acid exists in this structure. So this is the most protonated structure here. Clear? So whenever you are going to get any such questions where you have to calculate isoelectric pH for more than 3 groups, in that case first decide what is the lowest pH and then assume that you have put amino acid at the low pH than the lowest pH. So in this case lowest pH is 2.1. So I am thinking that I have put amino acid at pH less than 2.1, that is pH 1.5 or any one pH or any pH. At that particular pH, because this is most protonated condition will be existing. So in that case, this is having proton, this is having proton, this will can take extra proton, so I have added one extra proton. So at this particular pH, this amino acid exists in this structure, like you have COH and NH2 group. So at pH less than 2.1 means any pH like pH 1.5, it exists in this structure, that is protonated structure. Protonated structure means, can you tell me what is the total charge in this case we have? How much charge we are having? We have only one positive charge, no negative charge at all. So no charges here, no charges here, only amino group is having only one positive charge. So we have written one positive charge. Clear? Alkaline, yes, perfect. Yes. So now we are going to increase the pH from 1.5 towards higher side. So we have increased pH 1.5 to 2.1, and you know that at 2.1 pH this group is going to be dissociated. This will lose their H plus because its dissociation coefficient is 2.1. So at that 2.1 pH this H plus will be charged. So you have increased the pH from 1.2 to 2.1. As soon as pH will reach 2.1, this group has released their H plus, means it becomes negatively charged because it releases their H plus. Now you can see how much charge it is having. How much charge it have? It is having one positive here and one negative here. So overall charge is one positive, one negative. It means overall charge is 0. So I have put 0 charge. Nivans, not plus 2. Where is plus 2? It is having one positive here and one negative here. One negative, one positive. So total charge is 0. So I have put 0 charge. Now, so after at 2.1 pH, amino acid exists in this structure. See, at pH, this is, we have 3 pH. pH 2.1, pH 3 point something, and pH 9.9. So we have taken amino acid a pH which is less than 2.1. So any pH, either it will be 1.5, it will be 2, it will be 1.8, it will be 1, any pH less than 2.1. So at that particular pH, your amino acid will be in the most protonated forms. Most protonated form means maximum proton it will have. So this is protonated structure, this is protonated structure, and this is also protonated structure, means maximum H plus will be added there. You cannot add any extra pH in this one. H plus will not be added now. This is the maximum H plus will be there now. So in this structure at 1.5 or 1.8 whatever pH, any pH less than 2.1, it will exist in this structure. In this structure means it is having one positive charge. So one positive charge I have written here. Now I am going to increase the pH from 1.2 to higher side. Higher side means going towards upper right side. So as soon as I will reach to 2.1, this 2.1 pH is the dissociation constant, dissociation coefficient for this group. This group. So this group will dissociate, and how it is going to dissociate? It will release their H plus. So H plus has gone. So if H plus will go off, then what will happen? It will be COOH minus. So H plus has gone and it becomes COO minus. So here we had only one positive charge that I have written. Here one negative charge and one positive charge. So one positive and one negative. So overall charge is 0, and that I have written here 0 pH. Now I am going to increase pH 2.1 to higher side. So as soon as I will reach to 3.9 pH, because 3.9 is the dissociation constant for another group. So at this 3.9 pH, another group will dissociate. Another group will dissociate means this group's dissociation coefficient is 3.9. So at this particular pH, this group is going to release their H plus. So H has gone from there also. Now you can say what is the positive total charge in this one? 1 negative, 2 negative. So it is having 1 positive and 2 negative. So overall charge is 1 negative, means this can cross this one, so balance is 1 negative. So that I have written it. Is it clear? ये सबको क्लियर है? Perfect. Now again we are going to increase the pH to higher side. So as soon as I will reach to pH 9.8, at that particular pH the third group will dissociate, and third group is this one. So this will release their H plus. So one, if you are going to remove H plus from here, it will be NH2. Now you can see how much total charge it is having. So it is having 1 negative, 2 negative and 0 positive. So overall charge is -2. So this is just I have arranged, I have taken pH less than 2.1 up to highest pH. So all the three groups has dissociated, one at this pH, other one at this pH, third one at this pH, and this is the charge balances. So any pH which is less than 2.1, they will have one positive charge. Any means at 2.1 it will have this pH, like this is the arrangement. Yes, perfect. Now you just remember what was your definition for Zwitterion. So Zwitterion was the ions where we have equal number of positive charge and equal number of negative charge, and overall charge will be 0. So this is one compound which is having one positive charge, 0 charge, one negative charge, 2 negative charge. So according to Zwitterion definition, this is my Zwitterion forms, which is having equal number of positive charge, equal number of negative charge. So this structure is my Zwitterion. So this Zwitterion exists between two specific pH. What are the pH? That is pH 2.1 and pH 3.9. Electrically neutral. Yeah, this is electrically neutral. So this compound exists between two specific pH. One is 2.1 and second one is 3.9. So what we will do, we will take the average of this pH and this pH, means we will take the average of those two pH between which Zwitterion exists. So Zwitterion exists between 2.1 and 3.9. So we have taken the average of that two particular pH, and pH is value we have got it 3, means this amino acids isoelectric pH is 3, means at pH 3 it will be electrically neutral forms, it will exist in the Zwitterion forms. Similarly, you can see here, this is arginine. In this case, arginine is also having different ionizable groups. So in this case, these are the three ionizable groups, 1, 2, 3, and these are the three ionizable pH. So what we will do, in this case we have 3 pH, 1.8 to 8.99 and 12.5. So what we will do, we will take the amino acid any pH which is less than 1.82, means we will take it 1.5, we will take it 1, we can take it any other pH which is less than 1.88. So at that particular pH amino acid exists in the most protonated forms. This is most protonated forms. Proton is here, it cannot any extra proton, here is proton and here is extra proton. So this is the most protonated structure. So if you will see in this case, this compound is having, what is the charges? 1 positive charge, 2 positive charge. So any pH which is less than 1.8, that particular pH this compound exists, and this is having 2 positive charge. So first arrange all the 3 pH, then hypothetically tell your amino acid, take your amino acid at any pH which is less than the lowest pH. Think that particular pH, this will be in the most protonated forms, means maximum group will take their pH H plus. So this is having 2 positive charge. So because lowest pH was 1.8, so I have taken it to 1.51, any pH less than that one. Now I am going to increase the pH to 1.5 to 1.82. So what will happen? One of the group whose dissociation constant is 1.82, that will dissociate, and this is for this acid group. So they have dissociated here. You can see it here. Means it has lost their H plus. Now it is having how much charges? It is having 1 positive, 1 positive. So 2 positive, 1 negative. So 2 positive, 1 negative. So overall charge is 1 positive, and that we have written here. Clear? Now again we are going to increase the pH from 1.8 to 8.99. So at that particular pH, another group, either this group or this group, is going to be dissociated. Nivens, not -1. You have 2 positive charge, 1 negative charge. 2 positive and 1 negative. So overall how much you will get it? You have 2 positive and 1 negative. So what will be the balance? The balance will be +1. Okay, so we are going to take amino acid less pH than this one. So another group has been dissociated. Now you can see how much overall pH it is having. So it is having only 1 positive charge, 1 negative charge, means 1 positive, 1 negative, means it is 0. So 0 charge. Now again we have no, Ramina. See, 1 positive, 1 negative. Now we have taken again at higher pH at 12.5. So again this group will dissociate. So it will be NH2. Now it is having only 1 negative charge. So slowly, because we know that this group's dissociation constant is 1.8, this group's dissociation constant is 8.9, this group's dissociation constant is 12.5. So when you are going to increase pH 1.5 to 1.82, this group will dissociate because its dissociation constant is 1.8. When you have increased the pH at 8.99, this group will dissociate because its dissociation constant is 8.9. Again we have increased pH 8.99 to 12.5. This group will dissociate because their dissociation constant is 12.5. So you have to just arrange it in this sequential manner. First, make your amino acid in the most protonated structure, and then one by one remove proton from there. So we have arranged this one. Now according to our Zwitterion formula, which amino acid is the Zwitterion structure? This is 0 charges. So this is my Zwitterion. It is having 1 positive, 1 negative charge. So it is my Zwitterion. Now this Zwitterion exists between 2 specific pH, that is 8.99 and 12.5. So we have to take average of 8.99 and 12.5. So the average is 10.77. Means for this amino acid, the isoelectric pH is 10.74. Anusuya, what is +1? No. I am going to tell you the rules. First rule, arrange all the Ka values. Second, assume amino acid at lower pH than lowest Ka, and at that one it will be Is it clear? So first, when you have any amino acid which will have more than one groups, more than one dissociation, more than two dissociable groups, so first arrange all the pH values according to their Ka value. So you will have one highest value, one lowest value. Now assume amino acid at the lower pH than the lowest K value. Like in this case we had 3 pH value, that was 1.8, second was 8.9, third one was 12.5. So arrange them and then assume your amino acid at the lower pH than the lowest pK value. This is the lowest pK value. So I am assuming I have taken amino acid at the lower side, lower than 1.8. At that particular pH, amino acid will be in the most protonated forms, like COO will be in the form of COOH, NH2 will be NH3, so most protonated forms. So add protons to all the dissociable groups, either it will be COOH, it will be NH2, wherever it will be, and then slowly increase the pH, and as soon as you will reach here, one group will dissociate. As soon as you will reach to another pH, another group will dissociate. As soon as you will reach to third pH, another group will dissociate. So dissociate one by one and see how much charges are there. So once you have find the charges, then decide which one is your deuterion structure, and then say both side of the deuterion structure which pH is there. Then take the average of that two deuterions. Is it clear? So that we have done here. That we have done here. We have we have arranged 3 aminos, 3 pH. Now take an amino acid at any pH which is less than 1.82. Fine. So then see how much charges is there. Then we have slowly increased the pH to 1.8. One group will dissociate. Then we have seen the charges, how much charge is there. Then we have again increased the pH to come to this group. See how much charge is there. We have written it. Then again increase pH. See the charges, how much charge is there. Now according to my rule, this is my deuterion. So I will see both side of the deuterion. So this is this structure, this is this pH. So take the pH average of these two pH, and that will be your isoelectric pH. Which value, Anusuya? Between 2 and 3. See here, one positive charge, one negative charge. one positive charge. So it is having 2 positive, 1 negative. So overall it will be 1 positive. That I have written here. Because this group is going to dissociate at 12.5, this group will dissociate at 8.9, this group will dissociate at 1.8. So at 1.82 it exists in this structure. If you have increased this pH 1.82 to 8.99, so this group is going to dissociate. This group means this group has lost their, here you have 3 protons and N positive, 1 proton has been released, so it becomes NH2, means now it is having only 1 positive, 1 negative. So 1 positive, 1 negative means overall charge is 0. I have written it. Again, if you have increased the pH, so 12.5, at 12.5 this group will dissociate. So they have lost one of the proton and positive charge has gone. So whatever we have seen here, same thing we are going to plot in the form of graph, and that is called as titration curve. So in the titration curve, we are going to plot a graph like in the case of arginine. What structure we are going to see here? If I will plot a graph between 1.8, 8.9, 8.9 and 12.5. So this structure we are going to plot a graph 1, 2, 3, 4. So we are going to plot a graph here. So at 1.8 this, so somewhere between here we are having isoelectric pH. So whenever we are going to have a amino acid, in that one if you are going to add acid or base, charges going to change, charges is going to vary. And if you are going to plot a graph between the pH variations along with how much OH or acid you require, that is called as titration curve. So if you are able to draw that structure, what we have drawn for isoelectric pH, you can easily draw this titration curve for every amino acids. So that is not at all a different. Now come to the chemical properties due to amino acids, due to carboxylic groups. Because this is carboxylic acidic groups, so acid is having a property that it will react with base and give you salts. So acid reacts with base and give you salt. So here also acid group reacts with base and give you a salt. So that is one of the important properties of any acids. Second important properties of any acidic solutions are acid reacts with alcohol. So whenever acid reacts with alcohol, it will give you ester. We might have seen this one in case of fatty acid also. So fatty acid reacts with glycerol and gives you ester, that is your triglyceride. So there also we have Anusuya, which value? I'm not getting you. I'll do one thing. After this one, I will give you my numbers. You can send me WhatsApp whatever you want, because I'm not going to clear it. Second important reaction is decarboxylations. Decarboxylation means, as its name suggests, it is D means removal, carboxylation means carbon dioxide. So we are going to remove the carbon dioxide from the amino acid. So whenever we are going to remove carbon dioxide from amino acid, it is called as decarboxylation reactions. this for we have 20 amino acids, and this is your basic amino acid, a normal amino acids. In that case, if you are going to remove the carbon dioxide from here, so this CO2 will be removed. So ultimately we will get a amine derivative. Remove this COH, so it becomes RCH2 NH2, like this one. This is amine derivative. This decarboxylation reactions requires a decarboxylase enzyme. So we have 20 amino acids. So for every amino acid we require a specific decarboxylase enzyme. So 20 decarboxylase enzyme we require, like for glycine different decarboxylase enzyme, for alanine different decarboxylase enzyme. For every specific amino acid we require a specific decarboxylase enzyme. The thing you need to remember is, after decarboxylations, amino acid is going to give you corresponding amines. Like here, one of the example is we are having histidine. Histidine is an amino acid, basic amino acid. We know that we have 3 basic amino acids: arginine, histidine and lysine. Histidine is a basic amino acid. Here we are having histidine decarboxylase enzyme, which I have told you for every amino acid we require a specific enzymes. It removes the carbon dioxide from here. Ultimately we will get a histamine, that is a amine derivative of histidine. Similarly, we are having for another amino acid also, like glutamate gives you, after decarboxylations will give you gamma amino benzoic acid, that is normally negative neurotransmitter or inhibitory neurotransmitter. So here glutamate decarboxylase. Similarly, we are having tryptophan, which is going for decarboxylation reactions and ultimately gives you serotonin. So that is, decarboxylation reactions normally gives you amine derivative of the amino acids, and that compounds have some basic usage in our biochemistry, like signaling molecules or neurotransmitter forms or any other immunological responses. Like serotonin and histamines have immune systems, have some roles. They means they are involved in immune system functions. Next reaction of acids are, we are talking about acidic properties of acidic groups. So so here also we are having acidic group, here also we are having acidic group. So acid groups can also react with ammonia and ultimately gives you a amine derivatives, like we have already seen in case of classification, where glutamic acid and aspartic acids, acid groups reacts with ammonia, gives you amine derivative. So glutamic acid gives you glutamine, aspartic acid gives you asparagine. So that is the reaction of COOH group with the ammonia, and it gives you amine derivative of that particular compound. No issue, Anushya, you can tell me, you can send me. Whatever questions you can have, if even after this lecture we will have any question, you can send me. Then some of the properties of amino acids are due to their acid amino groups. Like amino group is a basic groups. This basic group reacts with acids. So this is base. It reacts with acids and gives you salt. So whenever acid reacts with base, it will give you salt. So there also we have seen COH group reacts with base, gives you salt. Here we have base reacts with acid, gives you salt. So it reacts with any of the minerals acids and gives you salt formation. So like amino group, which is a basic group, which is alkaline group, it reacts with any acids like HCl, HNO3, H2SO4 or any other acids, and ultimately gives you a salt. Salt formation will be there because of that is the basic nature of any bases. So any base reacts with any acids, gives you a salt. Second most important reaction in case of amino acids are reaction with ninhydrin. Ninhydrin is nothing, it is a compound. So normally we are going to use this ninhydrin test for the diagnostic purpose of amino acids. So we detect amino acids existence, alpha amino acid existence with the help of ninhydrin. So in that case, amino acid normally going to react with ninhydrin and gives you a purple color formation. We are going to see that particular details. So in that case, in this ninhydrin reactions, one alpha amino acid, wherever it will be, either it will be alone, it will be in the protein form, it will be in the glycoprotein, it will be in the any other forms. So wherever we are having alpha amino acid, it reacts with ninhydrin. This reaction occurs in two steps. The first step is, this is my first step. So alpha amino acid reacts with ninhydrin. Ninhydrin is converted into hydrin-dentane, that is the reduced form of ninhydrin, and amino acid converted into three molecules. So this is coming from your amino acid. Amino acid converted into aldehyde, ammonia and carbon dioxide. In the second reactions, this is my second reaction. This hydrin-dentane, this ammonia reacts with another molecule of ninhydrin. So first molecule of ninhydrin has been used here, and this is the second molecule of ninhydrin. So hydrin-dentane from the first reactions, ammonia from the first reactions, and ninhydrin, a fresh one, reacts here and gives you a colored compound that is called as Ruhmann's purple. It's diketohydrin-dentane. Yeah, it will give you pink, blue color depending on the concentration. I am coming there. So in this case, this color formation depends on how much ammonia is there, because this is insufficient amount. So as much as ammonia will be there, that much color will form. So if more ammonia is there, more intense color will be there. Less ammonia, less color. So this ammonia is we are going to get from here, and this ammonia formation depends on how much amino acid you are having. So if we have more amino acid, more alpha amino acid in the test solutions, if we are having more alpha amino acid in the test solutions, more ammonia will form, and if more ammonia will form, more purple color will form. So the color, what you are going to tell it, pink, purple or blue color, that depends on how much amino acid is there. So if structurally, if you say it, this is the reactions. So I have told you two reactions. First reaction is alpha amino acid reacts with hydrin and ninhydrin, gives you hydrin-dentane. Amino acid will be divided into three fragments: aldehyde, ammonia and carbon dioxide. So this is your ninhydrin molecules. This is amino acid. In this case, this CO2 will come here, this ammonia will come here, and this is going to form RCHO. So ninhydrin will be converted to hydrin-dentane. The changes which happens at this particular place, OH becomes H, means oxygen has gone. So removal of oxygen is called as reduction. So ninhydrin gone for reduction. So this is reduction, reduced product. This is reduced product of ninhydrin. So if you are going to get a question that what is hydrin-dentane, so it is a reduced product of ninhydrin, partially reduced product, and amino acid going to give you three fragments. In the second reactions, the hydrin-dentane which we have formed there, yes, it depends on amino acids. So this hydrin-dentane or ammonia which we have produced in the previous reactions reacts with ninhydrin, fresh ninhydrin, and gives you Ruhmann's purple. So here fresh ninhydrin, and from previous reactions ammonia and hydrin-dentane, ultimately these three reacts and give you this compound. This is called as Ruhmann's purple. Normally its color will be purple, otherwise it varies according to the intensity of the amino acids. So this is for all the amino acids. I have told you this is a test for alpha amino acids, but in our amino acids we have one amino acid also, that is proline. So all the compound normally gives you purple color, but proline gives you yellow color. So remember, that is the difference. Proline gives you yellow color, or remaining all amino acid normally gives you purple color. So this is the overall chemical reactions. Two molecule of ninhydrin reacts, one molecule in the first reaction, second molecule in the second reactions. So two molecule of ninhydrin reacts with amino acid divided into carbon dioxide, aldehyde and ammonia because it has been reacted with the here, so I have not written here. So overall, two molecule of ninhydrin reacts with amino acids, gives you remains purple, and ultimately forms carbon dioxide and aldehyde. And this color we are going to measure qualitatively as well as quantitatively. So whatever type of things you want, you can measure it. Clear? Next reaction is, we have two more reactions left. We will finish it fast. So one is called as deamination. Deamination means, D means removal, amination means ammonia. So whenever we are going to remove ammonia from the amino acid, we are going to call it deamination reactions. So deamination is the removal of amino group from the molecules. For every amino acids, we require a specific deaminase enzyme. In this case, we require a enzyme, it is called as deaminase enzyme. So for every amino acid, we have a specific deaminase enzyme. In our body, normally this deaminase enzyme or deamination reactions takes place mainly in the liver, but it can also occur in kidney. But main site is liver. If you have a questions where deamination reaction occurs, you have an option liver, kidney and other organs. Select liver. If only one option, you have to select it. So like this is the amino acid which is having central carbon amino group RH and CH group. In this case, if you are going to remove this group in the form of ammonia, which ultimately going to excrete in the form of urea, because ammonia is water insoluble, so we have to remove it from our body in the form of urea only, which is water soluble. So this has been removed, and this portion have different fates, different future. Either it will be metabolized into carbon dioxide and water, or it will be used as a glucose synthesis, or it will be in the acetyl coenzyme A formations, or it will be going to involve in the ketone body formation. Means it is having different fates. So this is called carbon skeleton. So when deamination reaction happens, ammonia will be excreted from your body in the form of urea through the urine, and remaining portion is going to utilize for different other purposes like carbon skeletons or any other purposes. So whenever we have a amino acid, if you are going to remove ammonia from the amino acid, we are going to get keto acid. So amino acid minus ammonia equal to keto acid, or you can call it keto acid plus ammonia equal to amino acid. We have different types of chemical reactions, different type of deamination reactions. Those deamination reactions can be either oxidative, reductive, hydrolytic or intramolecular. We're going to prepare talk another lectures sometime other time when we will talk details about deamination reactions. So just now, for deamination, every deamination reactions, for every amino acid we require a specific deaminase enzymes. So when you are going to remove ammonia from amino acid, it will give you a keto acid. And last reaction is transamination. Trans means transfer of ammonia group. It is not deamination, it is transferring. So in this case, we are going to transfer the amino group from one amino acid to the keto acid. Like in this case, we are having amino acid reacts with a keto acid. Amino acid reacts with keto acid. So this amino acid removes their ammonia This ammonia will be taken by this keto acid. So this amino acid, after the removal of ammonia, it will be converted into keto acid, and this ammonia will be taken by this keto acid, so it will be converted into amino acid. Means you are going to have a reaction between amino acid and keto acid, and product will be keto acid and amino acid. Means amino acid converted into keto acid and keto acid converted into amino acid. This is called as transamination reaction. Means transfer of ammonia from this amino acid to the keto acid, and it is going to happen vice versa. Like you can see here, this is amino acid, this is keto acid. This ammonia is going to be released from this one. So this amino acid converted into keto acid, and this ammonia will be taken by these molecules and it will be converted into keto acid. So now just remove this one. Here we are having amino acid. This amino acid removes their ammonia and it will be converted into keto acid. So ammonia has been released. This ammonia will be taken by this keto acid and it will be converted into amino acid. So there is a reaction between amino acid and the keto acid. Keto acid becomes amino acid and amino acid becomes keto acid. For every pair of amino acid and keto acid, whatever amino acid, whatever keto acid pair you are going to form, they require a specific enzymes. So the enzyme which we require here is called as transaminase enzyme. Transaminase enzyme. So for every pair of transamination reactions, we require a specific transaminase enzyme, and every transaminase enzyme requires a cofactor that is called as pyridoxal phosphate, PLP. Pyridoxal phosphate. This is vitamin B6. The role of this vitamin B6 is, this is associated with the lysine molecules, lysine amino acid of the enzyme. So this is just a carrier of transamination reactions. So this is just a carrier of this ammonia. So when this amino acid releases their ammonia, it will be taken by this PLP, pyridoxal phosphate, takes this ammonia and carry from here to here. So PLP of the transaminase carry ammonia from here to here. So it is a cofactor associated with the transaminase enzymes and help in the transfer of amino group from here to keto acids. This is called as transamination reactions. We have a separate video for the transaminations that you can see it. And this you need to remember. We have number of separate video for the different chemical reactions which we are using for the detection of different amino acids, like biuret test for peptide bonds, ninhydrin test for alpha amino acid, just now we have seen it, xanthoprotic test for benzene ring, all the aromatic amino acids, Millen's test, and the Folin category test. This one and this one for phenolic groups, means benzene ring with OH group, that is tyrosine. So tyrosine gives 2 test positive, that is Millen's test and Folin category test. Hopkins cold test for the tryptophan which is having indole ring. Sakaguchi test for guanidino group arginine. Nitroprusside and sulfur test for sulfhydryl group SH group, that is present with the cysteine, and poly test for imidazole ring which is present in the histidine. So this you need to remember. Yes, Nivans, perfect. So this is all about today. If any one of you have any issue, you can ask me on my number. If you have any query, any comments, anything, you can ask me on my number, on my WhatsApp. Any questions? Anyone is having any questions? Anusuya, you can ask me, you can send me a message what you want to ask. Is it fine? Whenever, wherever you are having any difficulty, because last portion I have gone little bit fast because it was too much time. So if you are having any issue in understanding, you can ask me, you can send me message. Okay, so thank you very much everyone. Thank you everyone for watching. Good night.